Okay? This story is helping you to understand Archimedes Principle, how it came into being. This is an incredibly important principle, and unless you understand density, you won't really be able to understand Archimedes' Principle. We kind of build on that idea. And the story of Archimedes' Principle goes back to a king by the name of King Hero. You've got to go back into ancient Greek times, you know, when they wore togas, you know, like bed sheets wrapped around their bodies. And they sat around and they thought deep thoughts. Well, this particular king was king of a kingdom that's now current modern-day Sicily, or Syracuse, was the name of his state, okay, his Greek state. And it's kind of like a city that gets so big that we call it a kingdom. Now, this wasn't the biggest of all the kingdoms. I'm sure you could think of a lot of other places around the world that were bigger at that time. Different kings that you might have heard of. You probably didn't hear of King Hero. And he was probably a little insecure too. You know, not the biggest king, not the biggest kingdom, kind of a short man, middle-aged, maybe going through a middle-age crisis. Now today, when men go through middle-age crisis, they maybe go out and buy some new clothes or a sports car to make them feel younger. King Hero, he wanted to have what every king would have, that would send a message to all his subjects that he was the best king in the world. What does every king have? That you can know that they're a king just by looking at them? Crown. A crown. So he wanted to have this crown fashioned for him, this beautiful grand crown, and then he wanted to show it off in a party. So he had this party planned for the next week. And he decided that he would take some of his riches, his gold, and he would turn them over to the goldsmith. Now, he took 10 pounds of gold, he gave it to the goldsmith and said, I want you to fashion this into the most beautiful crown ever. The crowns they made back then were not, you know, the pointy kind of crowns with jewels stuck on them like we think of in England later on. They were made to look like leaves. And then they were put together to form kind of a wreath that you would wear on your head. Anyway, he got the crown back from the goldsmith, got it back on Monday. His party was going to be on Friday. They dedicated this crown to the gods. That's what they did. And now it was a sacred item. And he thought, looked at himself in the mirror. I just look wonderful. I'm the best king ever. But like I said, King Hero was a little insecure, a little untrusting. And he started thinking, I'll bet that goldsmith ripped me off. I'll bet he didn't put all 10 pounds of gold into that crown. So what did he do? He took the crown and he took another block of 10 pounds of gold and he weighed them. He compared their weight on a balance. And guess what? It was the same weight. Does that mean the goldsmith didn't rip him off? What could he have done and still rip him off? No ideas? What do you think, Brianna?
Add cheaper metals.
Add cheaper metals. This was actually a pretty common practice. Think of it this way, okay? The king gives you 10 pounds of gold, says make a crown. And you know he's going to weigh it when you give him that crown. So you take 2 pounds of gold and you keep it for yourself. And then you add 2 pounds of something else. Copper, silver, some other metal, right? And you mix it in. Nobody's going to know, right? And then you make it into a wreath like that, the crown, and nobody's the wise. Well, this was fairly common, and the king kind of knew this. It's actually a common process that we do intentionally today. Because sometimes metals that are pure don't have the properties we want. Gold, for instance, if my ring were made of pure gold, I could take it off and I could just squeeze it, and it would flatten right out for me. Gold is a pretty soft metal. Now, it's valuable, but it's soft. We want to wear pretty gold jewelry, but we want it to be more durable. So what we do is we take some other metal and we add it to the gold. Pure gold is referred to as what? How many carats? 24 karat gold. Most of the gold you guys buy is what? 14 or better still. No, not usually 16. It's usually 18. 18, 10, sometimes 14. Okay? But those are the measurements that they usually do it in. The 10 karat gold would be the cheapest stuff. Less gold, more of the cheap metals. You know, like the necklaces you get at the swap meet that turn you green. Sometimes they're not even pure gold, or pure gold and something else. They're just covered in gold. just this thin little coating. Well, we want to do this. We want to add two metals together sometimes to get the properties of both. By adding copper to the gold, I make it somewhere between 10 and 18 karat gold. It's more durable than if it were just pure gold. Now, by the way, pure gold has more of a rich, deeper, darker, orangey kind of color to it, reddish orange color to it, than the gold that you guys are used to seeing, because that has copper added to it. Or we can make white gold. We add silver to it, and we make it white gold. But that's going to be cheaper than if we just made it out of pure gold. More durable, but cheaper. All of these are examples of alloys. Brass, you know, you got a trombone. That's made by mixing copper and zinc together. You get some new metal with a different property. Bronze is copper and tin. Pewter, you don't see as much of that now because people are afraid of lead, but those little heavy figurines, I don't know if you've ever seen any of these, they're really heavy and they look almost like they're black. They've been carved out of this stuff, it feels like it's metal. It is, it's tin and lead. And steel, like the legs on your desk. Those are steel, and that means they've been made from iron mixed with carbon. Iron alone would be heavier and not as strong, more brittle than if we add carbon to it. Now it's stronger and lighter, yes.
Is that pewter, the stuff that you use that black residue on your hand?
Yeah, you can. Don't lick it off. It's lead. You don't want lead. Okay? We know about lead paint and all that kind of stuff. It's not good for the brain. We'll talk more about stuff like that in a little bit. But anyway, these are all what we call alloys. And an alloy is a substance where we take two different things, we mix them together so we get a new substance with properties from both. Pretty, but durable. Get it? That's what we're doing here. So this was kind of a common practice, but it isn't what the king asked for. He wanted a crown made of pure gold. So, he had to solve this riddle. He just couldn't wear that crown in front of all the other kings and be embarrassed, have one of them come up and say, oh, that's fake. He had to be able to be confident that this was 100% pure gold. So he called in his science advisor, a man by the name of Archimedes. Archimedes, okay? Who's heard of him before? Archimedes is one of the most famous scientists of all time, and yet some people haven't heard of him because he goes way back. Brilliant, brilliant man. Look at 287 to 211 BC. You don't need to write that down, but long time ago. And he didn't just work on one kind of science. You know, like nowadays you're an astronomer, you're a chemist, you work on one kind of science. He did everything. He would work on machines for warfare, you know, how they could fight off their enemies with this technology that he would build. Ways of moving water, plumbing, all sorts of different machines. Just brilliant guy. And he had come through for the king on many other occasions, solved a lot of problems. So the king calls him into his chambers and he says, listen, Archimedes, I want you to test this crown and determine if it's pure gold. Archimedes says, oh, no problem. I'll just take it and I'll melt it down. Whoa, whoa, whoa. Can't melt it down. Number one, it's a sacred object now. Can't be destroyed. Number two, he needs it for his big party on Friday. There isn't time to make another one. So he needs to find out before that party if it is pure gold without damaging it. Well, there was no technology to do this at the time. Archimedes had to come up with that method. So the king says, don't fail me now, Archimedes. I've got to know if it's pure gold. Now this is a different kind of pressure. You've got to understand the time, okay? Head up, please. Head up, please. At that time, you know, the king is his boss. Now, if my boss gets mad with me, and Mr. Holmes gets mad with me, I have to go into his office and talk to him. He doesn't say, okay, Mr. Myers, I'm really disappointed in your performance. Please put your head down on the table. I lay my head down. And gets out a big hatchet or axe and chops my head right off, okay? Those aren't the kind of fears, head up please, that you have to have nowadays in the workplace. But when you have an all-powerful king that can say, chop his head off, if he gets mad at you, that's a little bit more pressure. You get my drift? So Archimedes goes home now, and he's trying to think up a solution. How can I get this crown? How can I measure this crown, test this crown to see if it's pure gold without destroying it? How can I keep my head attached to my shoulders? Because I don't want the king to be mad at me. So Archimedes thinks, and he thinks. and nothing's coming to him. Tuesday, Wednesday, now it's Thursday, the party's tomorrow, and he's got nothing. Now, you guys probably get a little anxious before tests, and then because of that nervousness, you can't think. As soon as you walk out of the test, suddenly all the answers come to you, right? Well, this is kind of how it was for Archimedes. He knew that he was stressed out. He knew that he was stressed out and that he wasn't able to think clearly, so he thought, well, maybe if I could just, calm down a little bit, the solution would come to me. So he did what a lot of people do today. They're stressed out, they go take a bath or something. So he had his bath filled with water. And he overfilled it. He filled it all the way to the top. Well, no big deal. All the houses were made of stone anyway. It didn't matter if the water got on the ground. So he goes to get into his tub. This is the famous sculpture of Archimedes. Same picture as you have up there. He goes to get into his tub, and he makes some common observations. But because he's such a brilliant man, he does something with them. He sits in the tub, and the water spills out. Big shot, right? He's displaced some of the water, just like we did in here. And as he sits in the tub, he looks at the water on the ground, and he thinks, man, that's a lot of water. I wonder how much that water weighs. Then he sits back, and he's trying to relax, and he realizes, oh, this is nice. It's nice being in a tub. I feel like I weigh less. That's right, I do weigh less. I wonder how much less I weigh. I wonder how much that water weighs. And if it had been a cartoon, ding, ding, a little light bulb would have come on over his head. He suddenly realizes that there is a connection between the water on the ground and how much less he weighs in the tub. He jumps up, goes running down the street, buck naked, screaming, "Eureka, Eureka," which in Greek means, "I have found it, I have found it." Just like the vacuum cleaner finds the dirt, okay? Screams, "Eureka, Eureka," as he's running down the streets, and everyone looks at, oh, there's old naked Archimedes again. He's so excited because, number one, he saved his own neck. He solved the king's problem. That's the second thing. And he actually came up with this principle, this idea. It's a math principle, but it's a concept, too, that allows us today not to just build a boat, stick it out there and say, okay, get on board, let's hope it doesn't sink. That's how the boats were done then, guys. Way back then, we build a boat and we just hope that it holds as much as we put on there. If it starts to go down, oh, better take some people off or some stuff off. How would you like to get on a cruise ship nowadays and have the guy tell you, well, we don't know if it's going to hold 1,000 people, maybe it will, maybe it won't, but come on board. I would want to have the assurance. Next time you're in an elevator, it has a little sign there, maximum capacity, 12 people. If it says maximum capacity, question mark, don't get on that elevator. That means nobody knows how many people it can actually carry. Maybe 2 will make it go crashing down. Maybe it can hold 30. They don't know. That's how things were built back then. Okay? But because of Archimedes' principle, today we can calculate precisely how much a ship can carry and know before we ever put it in the water. And that's exactly what you're going to do with the boats you're going to be making tomorrow. You're going to calculate how much they can carry and see how accurate Archimedes was and how accurate you will be with your prediction. So he went back to the king and he set up the following experiment. Not with giant beakers, okay, I didn't have the right clip art for this, but with big jars of water. He took the lump of gold, 10 pounds on this side, and the crown, 10 pounds on that side. We already knew that they balanced out. We already knew they were the same weight. And he filled up these jars with water, and he dropped those into the jars. Now, if they are the same mass, they balance out. Yes. But if they are different volumes, when we put them in the water, they're going to push out different amounts of water. You still with me? What he had figured out from his tub is that the more water you push out of the way, the more force water pushes back with it. I'll say that again. Don't write it down, just see if you get it here. He realized that in the tub, the more water you push out of the way, the more force water pushes back with it. Or maybe you can picture it this way. I take this ping pong ball, it takes some force to push that underwater. Ooh, I'm tired, right? But if I take a beach ball this big and I try to push it under a pool of water, it's going to take a lot more force. Why? Because I'm pushing more water out of the way. And not only did Archimedes figure out that bigger things push more water out of the way and therefore are going to have more force pushing back, but he figured out that everything weighs less in water. Even this weight, where's my weight go? Oh, here it is. Even this weight here, this one's kind of unimpressive. It's hard to see from your point of view. But if I hang this weight off of this, you can see that it's below the level of the tape, and if I put it in here in the water, it goes above the level of the tape, even when it's not sitting on the ground. Okay? Now, will this float? Of course not. It won't float. But what we know now from Archimedes is that everything, you put it in water, it's going to weigh less in water than it will in air. Why? Water's pushing back. And if I want water to push back more, I go from this size to beach ball size, right? If I want water to push back on this more, I shape it into a big boat. You still with me here? Like with the clay, remember when I did the clay before? Ball of clay won't float. Clay shaped into a big boat will float. Why? Because it pushes more water out of the way. Again, what he figured out is not only does it make this weigh less, but he could tell you exactly how much less it would weigh. This is how he did it. If you capture all that water that spilled out of his tub, and you take it over and you weigh it, let's say it weighs 20 pounds. That was the water that his body pushed out of the way, displaced. That water weighs 20 pounds. Guess how much less he weighs in water? 20 pounds. That is the force of water pushing up. And this explains why a boat can be made out of metal. A block of metal would sink right to the bottom. But you shape that metal into a bigger shape, bigger size, more volume. Now it pushes more water out of the way and it can float like a big aircraft carrier. So when he did this experiment, what he discovered when he did this for the king is that they were no longer balanced. The reason these are no longer balanced, they both weigh 10 pounds outside, right? But the reason they're no longer balanced here is because this was bigger than it should have been. Its volume was too big. And that meant that the water was pushing back with more force. So now since the water is pushing back more on this one than this one, that's why it's out of balance. Okay? So the goldsmith did rip him off, and the goldsmith never had to worry about another bad hair day. It's the end of the story. Okay? Archimedes made a huge discovery. Now, I'm using words like pushing down and pushing back. There's a word for water pushing up. That force of water pushing up is called the buoyant force. The force of the liquid pushing up is the buoyant force. So every time we try to put an object in a liquid and see if it floats, we got a force going down and a force going up. If the buoyant force is more than the force going down, we float. If it's less, we sink. Okay? So, what determines if something will float?
Its density.
Its density, absolutely. The density of the object and the density of the liquid. We are talking about things floating in water, because that's the most common substance. But are all forms of water the same? No. If this were salt water, would it be easier or harder to float in? Easier. It would push back with more force. Okay? I'm going to skip this next slide because you already answered that one. This is Archimedes' Principle written out, but maybe not in a way that you understand. If you want to write this one down, great. If you think you've got it here, that's fine too. Remember, the notes are for you. It says, if the buoyant force, that's the force of the water pushing up, is greater or equal to the weight of the object, it will float. So if the force going down and the force going up are equal, no movement. If the force going down is greater, we sink. If the force going up is greater, we float. It's that simple. Yes?
What happens if something overloads sand? Will it float
If something's density was the same, is that what you're saying?
Yeah, the water.
That's a good question, Matt, and someone asked me that earlier today, and the answer is a little complicated. You see, when I say the density of water is 1, I can change that density by heating it or cooling it, right? By heat it becomes what? More or less dense? Less dense. If I cool it, becomes more dense. And the truth is that the temperature of this water is different here at the surface than it is at the bottom. So if something has a density of 1 and I put it in here, it may not float at the top. It may float somewhere in the middle. See what I'm saying? In the ocean, salt water has a density of 1.4 grams per milliliter. That's an average. That doesn't mean everywhere it's equally salty. In some places it's going to have a lot more than that, other places it's going to have less than that. At the surface, the saltiness is different than at the bottom. So when we talk about things floating, it doesn't necessarily mean at the very tip top. Okay? So that's kind of a difficult question to answer. Alright, so like with this diver, you know, the old way of diving is you put some weight around your waist or on your ankles, and you go down, and then when you want to go back up, what do? Take off the weight. You're changing your density. By adding mass with very little volume, you increase your density and you go down. If you want to float at the surface like a little kid, you get your little ringy-dingy there, your inner tube, and you're not using that to add mass, you're using that to add volume. You add volume, and you're going to reduce your density. Okay? A sub and a fish work on the same principle. And now, scuba divers also use the same principle. They have a vest that works the same as this swim bladder for the fish, okay? Or the ballast tank for the sub. What the sub will do is at the surface, the tanks are filled with air. Then they use pumps to pump seawater into those tanks, increasing their density so they can go down. And then they pump that water back out to go back up. Fish do the same thing with a little swim bladder. Bladder is just a container that holds something. It's not just for pee. Okay? It can be for water, it can be for air. There's a bladder inside a football that holds the air inside. So we do the same thing with scuba diving. We have a vest that has little pockets for air, and we can either fill it with the air from our tank, or we can let the air out. And we can make ourselves more dense than water or less dense. We add more weight around our waist when we go scuba diving so we can get down. Then if we want to be less dense, we put air into our vest so we can go up. Okay? Now, this is where we get to the core of all this, of how this will directly apply to you here in class and the boats that we're going to be building. These words are kind of overwhelming. Okay? This first part is Archimedes Principle spelled out for you. This is Archimedes Principle as it applies to water. It depends on what you're floating in, okay? If I ask you, will this float? Your answer, Matt, wake up. Your answer is, I don't know. Why? You don't know because I didn't tell you what substance. Will this float in water? Yes. Will it float in alcohol? Don't know. You have to know the density of alcohol. Okay? We know that anything that floats in fresh water has a density that is less than 1. Not everything, here I'm going to black this out for a second, guys. Not everything has a density of less than 1. Some things are more dense. Some liquids are more dense. Salt water, 1.4. So you can float a lot better in salt water than you can in fresh water. There are even liquids that are metal. What am I thinking of? Mercury. That are even more dense than water. And just to kind of illustrate this, let me just give you an example. Have you heard of, I'm sure you've all heard of the story Alice in Wonderland? Okay. No? Never heard of that story? Have you heard of the character, the Mad Hatter? No? That's sad. These are classics, guys. And he wears the big hats and he acts all goofy and everything. Of course, everyone in Alice in Wonderland act pretty goofy. But let me just tell you how that character came into being. That hatters are people who make hats. And historically, when you make a hat, you use felt and you treat it with mercury. Mercury is a toxic metal. It's liquid at room temperature. And when you treat that hat with mercury, and you're using your bare hands, it goes through your skin, into your blood, and from there to brain cells and tissues that it can damage and destroy. If you're a hatter, if you're someone that works with this metal all the time, you will eventually go insane. That's what happened back in those days. So the character, the Mad Hatter, was based on real people who made hats that would get a little wacky after years of working with mercury. It is poisonous. So this next thing you wouldn't want to actually do, but it does sound kind of cool. Imagine you drain your pool, and now you fill it with mercury. Water has a density of 1. Mercury has a density of, I think it's like 13.6 or something. Let's see here. Yeah, 13.6. I was surprised. Okay? That's a lot more dense. You get that? Do you remember what our density was of lead?
Like 13.84.
No, I think it was less than that. I think it was, let's see if I have lead on here. I don't have lead on here, but I think it came out to like 11 or something. So we've got a liquid. Who would think of a liquid as being more dense than a solid? Not usually, right? You wouldn't think of it that way. So it's not about how hard something is. It's about how much stuff is in a certain amount of space. So that means that things are really packed tight in mercury. Okay, it takes some force to push this down. Imagine how hard it would be to push a beach ball under the surface of a pool of mercury. It's going to push back with 13 times as much force. Okay, you know how it hurts when you do a belly flop in the pool? Imagine doing that into a pool of mercury. You might as well just skip the pool altogether and do it on the concrete next to it, because that's pretty much what you're doing. So you jump into that pool of mercury, you're not going to hit the bottom, you're not going to go down a few feet, you're going to smack the surface, and then you can just start swimming there, right on the surface. Okay, with practically your whole body sticking out. Could you walk on it? Yeah. If you can keep your balance, you could walk on it. Okay? But the downside is, as soon as a little splash goes in your mouth and you get the toxic mercury poisoning, then you're going to go insane. But interesting thing to ponder. Yes.
Wasn't there some kid that like took mercury in like pill form and like went crazy from it after?
I think you're right. Was it a King Henry or something like that?
I don't know.
I think you're right.
Oh, he killed like 10.
All right. Now, guys, I don't really care whether you get the words written down. What's more important to me is that you get the concept. So if this means nothing to you, don't write it down. This is the simplest version I could come up with. It says, the buoyant force, freeze, buoyant force, what is that? The force of water pushing up. Okay. The buoyant force acting on an object, that would be like the boat. The force of water pushing up on the boat is equal to the mass of the liquid displaced. Liquid displaced would be the water pushed out of the way. Because the density of water is 1 gram for every milliliter, that makes our math real easy for water. Okay, so this is how the law applies specifically to water. Let's take an example here. You're going to make a boat in the shape of a little rectangle, something like this. Do you think you could find the volume of that rectangle? How would you do it? Yeah, but what would you do? Length times width times height. You get your 3 measurements and you multiply them together, right? If you know the volume of that boat and you know the mass of the boat, how would you find its mass? Put it on the triple beam balance. If you know those 2 things, not only will you be able to tell me will it float or sink, but you'll be able to tell me exactly how much cargo you can add. Here's how it works. So let's say I measured my boat, and it was 5 by 2 by 10. What's the volume? 100. 5 times 2 is 10. 10 times 10 is 100. Okay? Andrew, up here, please. So we found out that my boat takes up 100 milliliters of space. That's the volume of my boat. How much water, Matt, is my 100 milliliter boat going to push out of the way? Yeah, you do. I'll say it again. Listen carefully. How much water will my 100 milliliter boat push out of the way? 100 milliliters. You do understand that when this gets pushed into the water, it's going to push out an equal amount of water? This amount of water? The this takes up 100 milliliters of space and I push it into the water, it's going to push 100 milliliters out of the way? Yes? Okay. So now I know the volume of the water. The next step is, what do you know about water? How much does every milliliter of water weigh? 1 gram. So if every milliliter of water weighs 1 gram, how much is that water going to weigh that we're pushing out of the way? 100 grams. And that's what we call the buoyant force. In the example I gave with Archimedes, it was 20 pounds. I asked you, how much do you think that water weighs on the ground? He took it and he weighed it. It comes out to be 20 pounds. How much less does Archimedes weigh? 20 pounds. Okay? Don't get confused and think that this is always going to be the same. It is the same here because of a fact of water. We know that the density of water is 1 gram per milliliter. That means for every milliliter of water we push out of the way, water pushes back with 1 gram. So if this is 20, what am I going to have here? 50? 50. Got it? But let's just say that this isn't fresh water. Let's say that this is salt water. Salt water has a density of 1.4 grams per milliliter. What that's saying is that for every milliliter of salt water, it's going to push back 1.4 grams. Would this number be higher or lower?
Higher.
What would it be? Excellent. That's a star response. 140 grams. So we have more of a buoyant force. Again, guys, the buoyant force is the force of water pushing back. For our purposes in here, because we're using fresh water, if it's 100 milliliters of water displaced, it's 100 grams of water, that's also the buoyant force. Now, we've figured this all out by knowing the size of the boat. We also found the mass of the boat. Let's say we measured it and it came out to be 2 grams. Heck, it's made out of tin foil. It's not going to be too heavy. Okay, Andrew, tell me, if the boat weighs 2 grams, how much more cargo, what's the maximum amount of cargo I can add to it before it sinks? No, look at this now. This is the force going up. I have 120 grams of force going up. Right now I have 2 grams of force going down. So clearly it's going to float. I got more pushing up than pushing down. The question was, what's the maximum amount of cargo I can add before it sinks? Well, think it through, okay? This is the force going up. If I've got 100 going up and 2 going down, the 100's going to win, right? Okay. How much more can I add here before it's balanced out?
100?
No.
97? 98?
98. Now, just in case you were wondering, if you add 98 plus the 2, you have 100. That means you have 100 going down and 100 going up. Assuming your boat doesn't bend or flex or any of that, head up please, they're going to be canceled out. It'd be like arm wrestling and nobody wins, okay? But I will tell you that that boat will be right here at the surface. If you so much as throw somebody a BB, you're going to have more going down than going up, and the boat goes down. As soon as that boat starts taking on water, you're increasing its density, and it continues to sink rapidly. That's why things sink so quickly. Okay? So this is the kind of calculation that you're going to have to do. And you'll be able to predict precisely how much your boat can carry based on the volume and mass there. Okay? Any questions on this? All right, so the buoyant force is the force going up, and we got the weight going down. I'm going to show you on the homework here where you do a very similar kind of calculation. So that's it for the notes for right now. Before you start getting into your conversations, I need you to look at the back of this. This is just like the homework yesterday that you turned in that you did so poorly on. I'm going to try to point out some things that you're going to have questions about when you get home so that you won't make mistakes. The front of this has text that describes, again for you, Archimedes Principle. If you still don't get it after this lecture, you want to read through that. Okay? There's some things to define and some questions to answer in complete sentences. Make sure you do the front. There are questions on the front. Flip it to the back. I want to work you through some examples here on the table. Tiffany?
I was going to ask you for our boats. Are we going to be measuring them in the water?
You're going to be testing them.
Testing.
You're going to be measuring them with a ruler outside of the water and with a triple beam balance. All right, look at that table, okay? We've got 3 columns that we're having to fill in there. Buoyant force, sink or float, and weight in water. If you understand what I just went through with this example, you should be able to answer this. Okay, the weight of the object, that would be like our 2 grams here. That's the only force you're concerned with. We're not going to add any cargo. I'm just telling you, that's how much force we're pushing down with, okay? And then the second column says displacement weight of water. There's another name for that. What is it? You got it, the buoyant force. So for that first example, what is the buoyant force?
120 grams.
120 grams. Because that means we have 120 milliliters of water, and every milliliter weighs 1 gram. So the buoyant force for the first one is 120 grams. Okay? Now, if you know that, I think you can know what the rest of those are going to be in that column. And by the way, technically it shouldn't be 120 G. I'd like you to write 120 with a capital N after it. Does anyone know what the capital N stands for? That's a measurement of force. And for our purposes, it's going to be the same as the G. But the capital N is newtons. Never heard of that guy, huh? It talks about it on the front in the text if you actually read that. So that should be the label for that first column there, newtons. Now, if I've got 120 going up and 100 going down, am I going to sink or float? I'm going to float. You got more force going up than going down. You're going to float. You should write the entire word there, not an S or an F because you're too lazy. The entire word, float. The last one is the weight in water. You only do that if the item sinks. So you leave that blank if it floats. Let's look at the second example. Yes? If the force going down is greater than the force going up, it's going to sink. This one had 100 going down and 120 going up. That's how we knew it would float. Okay? Does that make sense?
Yeah.
More force going up than going down, you're going to float. Okay, let's do the second example. Anthony, you have a question? Okay, the second example. We've got 100 going down. And the buoyant force is what?
55.
55. Should have already filled that in. Going up. 100 going down, 55 going up. Are we going to sink or float?
Sink.
We're going to sink. Just like this sinks. But what people don't understand is that even though that sinks, it does weigh less in the water. Water is pushing back. It's just not winning. It's pushing back but not winning. So what would the weight of that particular thing be in the water? If water's pushing back 55, it's not enough to make it float, but it is pushing back 55. What would the weight be?
45.
45. Good. Hopefully you're not just going to randomly write down because you see a pattern here. Hopefully you understand the concept behind this. Okay, don't forget to answer any of the other questions that aren't just a short line, incomplete sentences, particularly on the front.